When I was in middle school, I discovered a free online graphing calculator called Desmos, and I spent hours just plugging in different things to see what shapes I could get. That's maybe a weird pastime, but I guess I'm a mathematician. Anyway, I naturally became well acquainted with the shapes of all the most common functions, and most of these shapes make sense if you stop and think about the functions for a second. But one exception to this is the factorial function, which completely defied my expectations and refused to make sense no matter how hard I thought about it. To make sure that we're all on the same page, the factorial of a number, denoted by an exclamation point, is the product of all the whole numbers up to and including that number. This is really not a complicated definition at all. Here are the first few factorials. Also, 0 factorial is 1, which is a bit weird, but we'll get to that later. Anyway, this definition only works if you plug a whole number into it. If I asked for 3.5 factorial, you can't multiply the first 3.5 whole numbers because that doesn't even make sense. So, the obvious graph of this function is just a collection of disconnected points. But evidently, mathematicians have found a way to extend this to any number, and apparently when you do so, this simple function turns into this not-so-simple shape. I spent a lot of time trying to understand where the shape came from, and it would be years before I found a satisfactory answer. So, the purpose of this video is to share that answer with you by deriving it from the ground up. But before we start, a couple quick notes. First, this video is sort of a sequel to my previous one, where I extended another sequence called the harmonic numbers to the reals. We'll be directly applying the process we learned in that video, but we'll have to add in a couple new techniques to make it work here. I'll still build it all from the ground up, so that video isn't a prerequisite to this one, but if you ever feel like you're missing some context, it might be worth giving it a watch. Second, if you've taken a decent amount of calculus, you might be familiar with this function. This is a representation of the solution we're looking for, and if you're familiar with integration by parts, it won't be too hard to prove this for yourself. But before you get mad at me for spoiling the ending, this is not the formula we will discover in this video. We will be deriving a completely different formula for the same function. See, even though it's easy to prove that this integral works, it's very hard to derive. It's normally handed down to you by your omniscient textbook, which doesn't really answer the question of where it came from in the first place. In my opinion, the journey is often more satisfying than the destination, so I'll derive the other form of the solution, which historically predates this one anyway. Alright, with that out of the way, let's get to solving. Our goal is to figure out how to extend the definition of the factorials to take in any number instead of just integers. Or visually, we're trying to connect all the points on the graph of the factorial in some natural way. Now, this is kind of an open-ended problem, because we could just draw any curve that passes through all the points, but then why would we have chosen that curve instead of any of the other infinitely many curves? How do we know which one is right? Well, hopefully this isn't too unsatisfying, but we'll decide what's right. Well, I'll decide what's right. You don't have a say, sorry. We'll discover a couple properties of the function that can be extended easily, and I will decree that our extension must adhere to those. But if I'm deciding what's right, what if you disagree with my decisions? Well, this doesn't mean that anyone is right or wrong about it. It just means that you might follow your instincts to find a different solution than the one I will. Remember that the fact that there are multiple solutions does not invalidate any of the cool math that arises from any one of them. So here's the first step. Remember that n factorial is equal to 1 times 2 times 3 all the way up to n. But take a look at all of these terms except for the last. This is just n minus 1 factorial. So we can substitute n minus 1 factorial in, and we're left with a neat little recursive formula. Given that we already know the factorial of one number, this formula can give us the next, or previous, factorial. For a quick example, if all that I know is that 4 factorial is 24, I can plug in 4 for n, and correctly see that 3 factorial is 6. Or I could plug in 5 for n, and it falls out that 5 factorial is 120. Remember how I mentioned that 0 factorial equals 1? Well, there are a couple explanations as to why, but in my opinion, this recursive formula gives the most natural explanation. Plug in 1 for n, and it falls out that 0 factorial must equal 1. Now, the reason I care about this formula so much is that it's really easy to extend it to any number. Just plug any number in. Now, to be clear, we cannot prove that this equation holds for non-integers, and that's simply because we don't yet have any definition of the factorials for non-integers. So this is actually my first subjective decision. I hereby decree that this formula should work for any number, integer or otherwise. To signify this leap, I'll replace the n's with x's. To see why this is useful, pretend that we've decided on the value of the factorial of some non-integer number. For example, I'll pretend that there's a point on the function right here. We can use this formula to find the points 1 unit to the left and 1 unit to the right. But then we can repeat it with these new points, and we can continue out as far as we want. Of course, I just chose this first point at random, so these are all wrong. But this demonstrates that the recursive formula dictates the values of infinitely many points from just one, no matter where that one point is. This is huge, because now all we need to do is decide on the curve for one interval 1 unit long, and as we sweep our point across it, the other points will trace out the rest of the function. Also, note that we've already introduced the craziness in the negative numbers. This is because when we try to find -1 factorial, we end up having to divide by 0, which introduces a vertical asymptote. And this division by 0 never disappears as we keep going to the left, so we see a repeated asymptote for every negative integer. We just saw how it's useful to repeatedly apply the recursive formula, but our lives would be a lot easier if we had a single expression that could do this in one step. We can derive such a formula like this. We make a bunch of copies of the recursive formula. In the first, we substitute x plus 1 for x. In the second, we substitute x plus 2, in the third, x plus 3, and so on. Now, each formula references the one above it. For example, the x plus 2 line has x plus 1 factorial in it. So we can substitute the first line in. And then, the next line has x plus 2 factorial in it, so we can do it again, and so on. We can repeat as many times as we want, but I'm going to stop after 5 so I don't run out of space. The pattern should be pretty clear here. To get x plus 5 factorial, we start with x factorial, then multiply by x plus 1, then x plus 2, and keep going until x plus 5. We can condense this process by writing it like this, and finally, since the pattern is clear, I'll just replace the 5 with an n. I like to call this the super recursive formula, but that's not a term you're going to find in a textbook. This notation is a little less common than summation notation, so I guess I'll formally introduce it. This symbol is the Greek letter pi. Well, it's the capital pi. The lowercase version is more famous. But this notation has nothing to do with circumferences or areas of circles. When written like this, it means to evaluate f at all the whole numbers from a to b, and to multiply them all together. So it's the exact same thing as the more common sigma notation, except with multiplication instead of addition. In fact, pi is the Greek version of p for product, and sigma is the Greek version of s for sum. Which isn't really important, but the more you know, right? Anyway, so far we've been doing exactly what we did with the harmonic numbers. And with the harmonic numbers, the next step was to notice that as we moved really far to the right, the points all flattened out, and we could use that observation to fully extend the function. But when we try this with the factorials, things don't quite work the same way. When we move to the right, it doesn't take too long to realize we have a problem. The factorial function does not flatten out. In fact, it does the exact opposite. It grows incredibly fast. It takes all this time just to reach 5 factorial, and it only grows faster from there. Even if I squish the graph way down so that the previous values are all on the screen, 6 factorial is still through the roof. Here's another way to put into perspective how huge the factorials are. 10 factorial is well into the millions. 70 factorial is, well, too big to fit on the screen. In fact, it has 100 digits, making it bigger than one Google. This is so huge that your fancy handheld graphing calculator will probably throw an error when you try to compute it. Obviously, we need some way to tame the beast. Well, when you think about it, the reason the factorials grow so fast is because they are repeated multiplication. Every time you multiply by a number, you're multiplying the cumulative effect of all the other numbers you've already multiplied. So, of course, it spirals out of control. If we were instead adding a number each time, we would expect something much more reasonable. But what good does it do to dream about having a sum instead of a product? The factorials are defined as a product, and that's that. Or is it? There actually is a tool that turns products into sums. The logarithm. Any logarithm will do, but I'll use the natural logarithm, which we write as ln of x. I'm not going to give a big lecture on logarithms, but in case you're a bit rusty, the natural logarithm is the inverse of the exponential function e to the x. Exponentials have these two properties, and from these, we can derive these two properties of logarithms. This first property is the one we want right now. A multiplication inside the logarithm is equal to a sum of logarithms. So here's what we'll do. We can take the log of the factorial, and applying this rule, all the multiplications become additions between the logs. I'll use sigma notation to condense the sum. Now I can do the same for the recursive formula as well. And finally, I'll give the same treatment to the super recursive formula. Naturally, turning products into sums turns pi notation into sigma notation. So now we have a completely new set of equations with additions instead of multiplications. Since these all describe the log of n factorial, I'll call the log of n factorial capital L of n, just to clean up our equations a bit. So here's the goal. We'll try to find a way to extend capital L of n, and then we'll be able to exponentiate it, which will undo the logarithm and leave us with the factorials. So graphing our L function, we can already see that it's much better behaved than the factorials were. Sure, it doesn't flatten out, so it'll be a bit tougher than the harmonic numbers, but it grows at a pretty reasonable rate. In fact, the further I go, the more the points seem to approach a perfectly straight line. This is actually the observation that allows us to define the factorial for non-integers. After all, it's really easy to extend a line to the reals, just draw a straight line through the dots. Once again, I can't prove that a line is the one true solution, because any periodic shape would fit perfectly well with all the equations we have so far. So this will be another subjective decision on my part. To symbolically express this linearity, note that on a line, the height difference between any two adjacent points is equal. If we can calculate this slope, we can multiply it by the horizontal distance from a known point, and we get the value of any point on the line. Now, we still need to prove that our L function really does become linear. We've moved pretty far on this graph, so I'll call the horizontal position of this point capital N. Capital N is just a placeholder for an arbitrarily large integer. Now, if we plug big N into the recursive formula, we get that the height difference between this point and its predecessor is the natural log of capital N. And doing this for the next few points yields the log of n plus 1, the log of n plus 2, and so on. So we can say that these points are all pretty much in a line if their height differences, these logarithms, are all pretty much equal to each other. It's tempting to do this by taking the limit of the natural log of n as n approaches infinity, but there's one slight issue. This limit doesn't actually exist. Logarithms do grow extremely slowly, but they still never stop creeping up without bound. This means that the slope of our function sort of gets infinitely steep, which sadly means our geometric intuition has kind of reached its end. But fret not, there's still a precise sense in which these logarithms are all pretty much equal. I'll condense this whole expression by saying that the log of n is approximately equal to the log of n plus k, where k is a decently small integer. What we can do is take the limit of the difference between the two sides as n goes to infinity, and if this limit is 0, that gives us a precise sense in which these two logarithms are pretty much equal. Now, I've already shown that adding two logarithms is the same as multiplying their contents, but it's also true that subtracting two logarithms is the same as dividing their contents. We can then do a little bit of fiddling and we're left with the log of 1 plus k over n. As n increases without bound, the k becomes negligible compared to it, so we're left with just the log of 1, which is equal to 0. So there, we've proved that these logarithms are pretty much equal. Alright, we're almost there. Let's plug in capital N for x in our super recursive formula. This gives us the value of our function for any point after capital N. But see how we have the log of big N plus k inside of this sum? This is what we just showed is pretty much equal to the log of big N, so we can just substitute that in, giving us our linear approximation. And with that done, the sigma notation becomes overkill. We're just adding the log of big N to itself, little n times, which is precisely the same as multiplying it by little n. And just like magic, this formula no longer requires little n to be an integer. Once again, this isn't something we can prove, so I hereby decree that this holds for any number. And to signify this, I'll once again replace the little n's with x's. And now, we're just a few manipulations away from an extended definition of capital L. We'll substitute in the super recursive formula for L of n plus x, and we'll substitute in the original definition of L for L of n. Then we can move things around a bit to isolate the L of x. Since these two summations both go from 1 to n, we can combine them, and then we can use our log subtraction division trick to make it a bit nicer. Finally, to express the fact that this approximation gets better and better as n gets larger, we take the limit as n goes to infinity, and then it becomes a true equality. Now, go ahead and breathe a sigh of relief, because we did it. We have a formula for capital L that works for any x. But before I move on, I want to point out that I used a squiggly equals sign, and then I just asserted that it becomes a true equality as n approaches infinity. If that makes you a bit uncomfortable, don't worry. I did it this way in hopes that the motivation for all the steps would be a bit more clear. You can do this more rigorously, but you have to do kind of a complicated dance with limits of differences, and it's much harder to understand the why behind it. But if you really want to see the whole process, I've got you covered. Feel free to pause and verify each step, or if you're less hardcore, just sit back and enjoy the animations. Alright, we have our solution, let's graph it. As I plug in larger values for n, the curve becomes closer and closer to the points, and in the limit, it interpolates them perfectly. So now that we've solved our L function, we're pretty much done. Remember that this is the natural log of the factorial function. To undo a logarithm, just exponentiate it. And finally, we can use the properties of exponents to make this formula less ugly. This x log of n turns into n to the x, and remembering that the logarithm turned our product into a sum of logs, exponentiating turns this sum of logs into a product. And with that, we've got our beautiful generalized formula for x factorial. To quickly recap what we constrained to get this one solution, our solution is the only function that matches the normal factorials on some point, adheres to the recursive formula for all x, and has a logarithm that becomes more like a line as x gets larger. To be mathematical about this last point, we could write it as this limit that we came across in our derivation. Or, one neater way would be to say that the second derivative of the log of the factorial must approach 0. But the standard condition that you'll likely see in textbooks is that the function must be logarithmically convex for positive x. A function is logarithmically convex if its logarithm is convex. Go figure. This is just a fancy way of saying that the second derivative of its logarithm is positive. Now, it's not super obvious that this condition locks us into the same function, but I have other things I'd like to get to, so I guess I'll leave this as an exercise for anyone who wants to try it out. Now, I'd love to take credit for this function, but I missed my shot by a couple hundred years. The interpolation of the factorials is often attributed to Leonard Euler, who published the result in 1729. You might recognize this name. He's one of the biggest superstars of math. In fact, it's joked that we name things after the second person who discovered them, because the first person is always Euler. But actually, in this case, Euler was the second person. The first officially written solution was by his friend Daniel Bernoulli, who beat him to the punch by literally 1 week. Bernoulli's solution is a bit of a variation, and it actually converges faster too, though at the cost of being more complicated. But Euler went further. He wanted to find an expression that used an integral instead of an infinite product. And sure enough, after a few months, he published this beautiful result. And this can be transformed by a simple u substitution into the integral that I teased at the beginning of the video. Now, to prove that these two expressions are actually equal is not an easy task. Or, if there is an easy way, it's escaped me so far. But for the rest of this video at least, I'll continue using the product definition. Now, the extended factorials usually aren't denoted by an exclamation mark. You might see capital Pi of x instead. But far more common is the gamma function, which is the same thing, just shifted 1 unit to the right. From my searching on the internet, it seems to be up for debate whether this actually makes things prettier or messier. But at least for this video, the pi function is cleaner because we don't have these x minus 1s everywhere. I'll also still use the exclamation point, just because we're used to it, and I'm making the video, so I make the rules. There's one last really cool thing I want to share, and it reveals itself when we take the logarithmic derivative of our function. The logarithmic derivative is the derivative of the logarithm, as you might guess. This may seem like a random thing to do, but remember, this is what we'd have to do if we wanted to prove that our function is logarithmically convex. Anyway, recall that the logarithm of the factorial is just our L function. So we can substitute our solution for the L function, and then take the derivative from there. Now, it's not too hard to carry this out. We just have to distribute the derivatives throughout, and then the x log of n becomes log of n. Now we can split up the logarithms in the sum, and this first one is just a constant, so its derivative vanishes. For the second one, the derivative of the natural log of x is just 1 over x, so we get 1 over x plus k. Now here is where a miracle happens. I'm going to bring up the topic of my last video, the harmonic numbers, just one last time. The nth harmonic number is defined as the sum of the first n reciprocals, which we can write like this. In my last video, we found that this formula extends that definition to non-integers. But notice that the harmonic numbers and the logarithmic derivative of the factorials both have this minus 1 over x plus k in this sum. It's kind of looking like there might be a connection here. So I'm going to do the classic trick of add and subtract the same thing to introduce this sum into our formula. The reason I did that is so that I can combine these two sums, and now I've introduced the harmonic numbers into our expression. And this leftover sum is just the plain old discrete harmonic number of n. But now that h of x doesn't depend on n anymore, I can take it out of the limit. But now if we look at what's left in the limit, that only depends on n and not on x at all, which means it must be a constant. I'll represent this constant with the Greek letter gamma, and if we calculate it, we find that it's about 0.577. Bringing this constant back into our expression, we get one of my favorite plot twists in math. The logarithmic derivative of the factorial function is the harmonic numbers minus this constant. At the end of my last video, I mentioned that the harmonic numbers are a shifted copy of a function called the digamma function. Well, what that function is defined as is the logarithmic derivative of the gamma function, so that's where the connection comes from. Now, this gamma constant was first discovered by, you guessed it, Leonhard Euler, so it's often called Euler's constant, though its full name is the Euler-Mascheroni constant, which adds the name of the mathematician who first calculated it to 32 decimal places. Now, it's natural to ask, is this number rational? Is it transcendental? Can it be made from some combination of e and pi and numbers like that? Actually, nobody knows. This is an especially mysterious number because it hasn't yet been proven if it's rational or not. Now, there's a lot more that can be said about this constant and the factorials and the harmonic numbers, a little bit of which is even within my understanding. But I think this is a pretty good place to end things for now. I think I've shown enough cool math, and I've definitely given myself enough editing work to do. So, if you made it this far, thanks for watching. I'll see you in the next video.